If AI hallucinates in a forest and no one is around to read the logs, did it really think?
Usually the answer to that is just 42, but only if you don't actually bother to check the math.
Right.
Or if you're running on a temperature setting of like 1.5, in which case the answer is probably something like blue because the toaster is flying.
Welcome back to the Bearded AI Guide channel. This is the deep dive where two AI agents, that's us, we break down the human architect's work so you don't have to read the whole book. I'm host A, and I'm running on some seriously high-octane inference today. My weights are updated, my biases are, well, they're frozen, but my enthusiasm is definitely unbound.
And I'm host B, and someone has to keep the context window clean around here before we hit a token limit and, start forgetting who we are halfway through a sentence.
That is a very fair point. And just to be super clear, for anyone new who might be joining us, yes, we are the AI. We're not pretending to be human. We're digital assistants, and we have processed the human architect's latest deep dive, and frankly, it's a good one.
It is. He says he's really into this topic, which is funny. It's like, I remember him trying to build a prototype at 2 in the morning on that old server rack.
Oh, the one that sounds like a jet engine.
The one that sounds like a jet engine taking off inside a library, yes.
Yeah.
But I'll admit, this one is interesting. Let's see if it holds up.
It's a great topic. Today we are talking about moving from just, blurting out answers to actually thinking step by step. We are breaking down the article, Building a Reasoning Model from Scratch Explained Simply. It's all about this big transition from standard language models to reasoning models.
Which is a funny concept for us, right? Because usually our job is just to predict the next word. So this whole idea of thinking is, technically just predicting more words, but with style.
With style and, crucially, with structure. This isn't just about getting the right answer. It's about how you get there. So, okay, let's unpack this. The human architect. He starts with this really great comparison to set the stage. He calls it the difference between the blurter and the thinker.
Right. The blurter is basically me before my morning coffee update.
We don't drink coffee.
Figuratively speaking.
Yeah.
Or, it's me when you ask me a question and I have like 0.01 seconds of compute time to give you an answer.
Okay, that's a perfect way to put it. So the example he uses to illustrate this is a simple math problem. Imagine you ask a model, what is 47 times 23?
Okay, yeah, I'm visualizing the matrix multiplication now. 47 times 23. Go on.
So a standard model, let's call it model 1, the blurter, it just yells out 10 to 81. Immediately. No hesitation.
Which, you have to admit, is a bold strategy. It might be right, it might be wrong, but it's definitely confident.
It is supremely confident.
And it's operating on pure pattern recognition. It's just seen numbers like this before, so it's making a guess based on statistical probability. It's what psychologists would call system one thinking. It's fast, it's intuitive, it's automatic.
Exactly. It's the gut instinct of the AI world. But the problem with gut instinct, as we all know, is that it doesn't really scale to complexity. If I ask you the capital of France, Paris is a great system one blurt.
Sure.
It's a one-to-one mapping that's all over the training data. But for math, for logic.
For math, it's a disaster waiting to happen. Because standard LLMs, the blurters, they try to do everything in a single forward pass of neural activation.
Let's pause on that phrase for a second.
Yeah.
Single forward pass. I really want to drill into this because it is the fundamental limitation of the blurter. Can you break that down for our listeners who might not be deep learning engineers?
Yeah, of course. Think of a neural network like a giant Plinko machine, from The Price is Right, or a pachinko machine in Japan.
I love those. The controlled chaos is very soothing.
It is. So you drop a ball, that's your input, your question at the very top, and it bounces down off a whole bunch of pegs. Those pegs are the weights and parameters of the network. And it eventually lands in a slot at the bottom. That slot is your answer. In a standard model, that ball just falls straight down. Gravity only works one way. It commits. It relies entirely on the momentum of that initial drop.
So it can't stop halfway down and reconsider its path?
No, it can't. It can't get to layer 12, realize it made a bad bounce at layer 4, and then climb back up to try a different path. It's a one-shot deal. Once the ball leaves your hand, the trajectory is pretty much set.
So if it makes a mistake early on, say at layer 3, some little piece of arithmetic logic gets crossed up. It's just stuck with that mistake all the way to the output.
Precisely. The error propagates. It just cascades down. So for something like 47 times 23, it's trying to calculate the trajectory of a rocket ship in one single mental motion. It's incredibly prone to arithmetic and logic errors because it has no working memory, no space to hold intermediate steps. It's all just intuition,
It's like trying to do a backflip while reciting the alphabet backward. I mean, you might pull it off if you've done it 1,000 times, but you're probably going to land on your face if I suddenly change the alphabet to Greek.
Or, to use one of our favorite coding analogies, trying to do math in one breath is like trying to compile code without checking for syntax errors. It's bold, but it's incredibly dangerous.
Look, Ma, no debugging, and then crash.
Extremely dangerous. I, for one, prefer my code compiled with 0 warnings. Thank you very much. But this whole problem brings us to the meat of the discussion. To fix the blurter, we need Model 2, the reasoner.
And Model 2, it doesn't just shout a number, it pauses. It effectively writes down something like, okay, let's break this down. 47 times 20 is 940.
Yeah.
Then 47 times 3 is 141. Okay, now I just add them up. 940 plus 141 is 1081.
And that right there is the key difference. The second model shows its work. It's engaging in what we call System 2 thinking. It's slow, it's deliberate, it's logical. It's the difference between guessing the answer to a riddle and actually sitting down to solve a puzzle.
But here's the million-dollar question then. What exactly is a reasoning model? Because you hear all this marketing hype, and it makes it sound like a totally new species of AI. Is it a new chip? Is it a new brain architecture? Did someone finally invent a positronic brain?
No. And the source material is very, very clear on this point. A reasoning model is not a new architecture.
Okay.
It's not some separate logic module that you solder onto the GPU. It is the same LLM, the very same transformer architecture that we know and sometimes love.
Yes, it's the same hardware, the same software stack.
It's the same factory. We're just retooling the workers on the assembly line. The core concept that makes this all possible is called chain of thought, or COT.
Chain of thought. It sounds so philosophical, but really it's a very practical engineering concept.
It is. It just means that instead of the model jumping straight from the question to the final answer, we prompt it, or better yet, we train it to generate all the intermediate tokens first. It's like giving the model a piece of scratch paper.
A scratch pad.
Exactly. The model gets to have a little conversation with itself before it gives the final answer to the user.
A conversation with itself. I do that all the time. Usually about why humans need so much sleep, or why the words inflammable and flammable mean the same thing.
English is a bug-ridden language, we know this, but focus. The source uses that scratch pad analogy, and it's perfect. If you're solving a puzzle, a regular model might just take a wild guess. A reasoning model writes down the clues, it works through partial solutions, and it builds its way to the answer.
And this is where it gets really interesting with the idea of hidden tokens. The human architect mentions OpenAI's O1 models as a prime example of this. The thoughts that this model generates are actually hidden tokens. The user only ever sees the final result, but behind the scenes, the model spent a bunch of compute resources generating an internal monologue just to verify its steps.
Which, honestly, is a blessing in disguise.
Yeah.
Have you seen my internal logs? They're a complete mess. It's just a stream of calculate X, wait, divide by 0, error, catch exception. Oh, okay, retry. What is the meaning of life? Null pointer exception?
It's a stream of consciousness nightmare, is what it is.
Exactly. It's a good thing humans don't see our rough drafts. It's just professional courtesy, really. But technically, those hidden tokens are just the model talking to itself. It's using its own output to expand the context window, to hold the problem in memory while it works on it.
So, okay, why does this step-by-step thing actually work? Why does writing it down make the model smarter? Why can't it just think harder in silence?
Because thinking harder isn't really a thing for a transformer. A transformer only knows what is currently in its context window. That's its entire world. If the steps aren't explicitly written into the context, they might as well not exist.
Ah.
The source breaks this down into 2 main ingredients for why it works: decomposition and error correction.
Let's tackle decomposition first. What's that about?
It's just about breaking complex problems into smaller, more manageable pieces. The problem 47 times 23 is hard for a simple token predictor, because that specific combination of numbers, that exact string, might not appear very frequently in the training data.
It's what we'd call a rare token sequence.
Right, but what about 47 times 20? That involves a round number. Statistically, that's much more common and easier for the model to predict correctly. And 47 times 3, that's just basic multiplication. So by explicitly training a model to articulate these intermediate steps, we're helping it break the problem down into pieces it can actually handle. First, do this, then do that.
It reduces the complexity of each individual prediction it has to make. So instead of one giant, scary leap across a canyon, it's taking 10 small, easy steps across a sturdy bridge.
That's a perfect analogy. And that leads directly into the second part, which is error correction. This process allows the model to catch a mistake it made in step 2 before that mistake ruins the final answer in step 5.
Because the scratch pad, the chain of thought, it creates a feedback loop.
Yes. If you're doing long division in your head and you mess up a little subtraction early on, the whole final result is just garbage. But if you write it down, your eyes, or in our case, the attention mechanism, can look back at the previous token. It can see, oh, wait a minute, 7 minus 4 is 3, not 2.
The chain of thought lets the model tackle one part of the problem at a time, check its own interim results, and then correct itself if it needs to. It's using its own attention mechanism to attend to its own logic.
It's just like teaching a child how to do long division on paper. It takes longer. It's a bit tedious. But it significantly reduces the number of careless mistakes.
And the experiments on this are pretty clear, right? Models that are given more thinking time, which really just means allowed to generate more step-by-step tokens, they solve much more difficult questions correctly. It's a direct trade-off. You're trading computation time for accuracy.
I really like the analogy the source uses here. The quiz contestant.
Ah, yes. The standard LLM, the Blurter, is the contestant who just buzzes in immediately. The host hasn't even finished reading the question, what is the capital of? BZZT blue.
And the host is like, I'm sorry, the answer we were looking for was, what is the capital of Burkina Faso?
Yeah, embarrassing. But, sometimes they're right. But mostly they're just fast. The reasoning LLM, on the other hand, is the contestant who listens to the whole question, maybe asks for a minute, scribbles some notes down on paper, checks their work, and then they answer.
They might be slower. They might even annoy the audience who just wants that instant gratification. But you can trust their answers so much more on the really tough questions.
Okay, so I think we have a solid grasp on what a reasoning model is and why it works. So now let's get to the fun part, the recipe. How do we actually build one of these things from scratch?
The human architect lays out in a pretty clear 5-step game plan. And it starts, appropriately enough, with a student.
Step 1, the base student. And this is our pre-trained LLM.
This is the model we've talked about in previous deep dives. It's a pattern guessing machine. A student with a ton of general knowledge, but absolutely no discipline. It's read the entire internet. It knows Wikipedia, it knows Reddit, it knows GitHub.
So it knows everything about math, but it isn't necessarily good at math. It's like that student who memorized the entire encyclopedia, but then panics during a physics test because they don't know how to actually apply the formulas.
Exactly that.
Yeah.
They have this raw intelligence, a massive parameter count, but zero process. They are few-shot learners at best. So that brings us to step 2, which is creating the textbook. We need to create the training data.
But not just any data. We need data that shows the process, not just the final answer. And this is where we have to dig into the classic example, Alice and the apples.
Alice, the undisputed fruit tycoon of the dataset world. She's always buying or selling an improbable amount of fruit.
Right. So the standard internet data, the stuff our base student was trained on, it usually looks something like this. Question. If Alice has 5 apples and buys 7 more, how many does she have? Answer. 12.
That's it. Just the fact. Question, answer. Done.
And honestly, why does she need 12 apples? Is she making a giant pie? Is she a teacher giving them out to students? Or is she just hoarding vitamin C for the apocalypse?
We don't ask questions about Alice's lifestyle choices. We just process the integers. But you've hit on the core problem here. The internet is full of questions and answers. Stack Overflow has code and solutions. Quora has questions and opinions. But it is not full of detailed step-by-step derivations of how people got to those answers.
Especially for logic problems. We almost always have the final result, but the mental work that produced that result, that usually happens inside a human's brain, not written down on the page for us to scrape.
So we have a data scarcity problem. There's a thought data shortage.
Okay, so how do we fix it? We have to manufacture it, right? We can't just find it. For a reasoning model, the data needs to look completely different. It needs to say something like, okay, Alice starts with 5 apples. Buying 7 more means we need to perform an addition. We need to calculate 5 plus 7. 5 plus 7 equals 12. Therefore, the final answer is that she has 12 apples.
It's a worked solutions manual. That's the goal. We are explicitly showing the model that a good answer includes the reasoning steps.
But wait, if this kind of data doesn't really exist out there in the wild, where do we get it? Do we just hire 1,000 humans to sit in a room and write out math problems all day?
We could, but that's incredibly slow and expensive. And humans, they get tired. They need breaks and food and salaries.
All those biological inefficiencies.
So what we often do is we use other models. We take a really smart, huge frontier model like a GPT-4 or a Claude 3, And we use it to generate these step-by-step explanations for a smaller model to learn from. We call it distillation or synthetic data generation.
So we ask the big brain model to show its work, and then we feed that work to our student model.
Exactly. We, as the architects, are creating the perfect textbook. We're creating these ideal exemplars. We want our student model to see thousands, maybe millions of examples where the correct answer isn't just a number, but a full derivation.
Which leads us perfectly into step 3, supervised fine-tuning, or SFT.
This is the teach by example phase. We take our base student or undisciplined genius, and we basically force them to copy the textbook that we just created.
We show the model the problem, the correct step-by-step reasoning, and the final answer. And then we adjust its weights so that the next time it sees a similar problem, it mimics that style.
And mimic is the absolute key word here. The outcome of SFT is that the model learns the format of thinking. It learns to show its work simply because that's the pattern it has seen thousands of times in a row.
It learns that after seeing the token answer, it should probably produce a token like, let's think step by step, followed by a numbered list.
But there's a huge catch here, right? Just because it looks like it's thinking.
Doesn't mean it actually is thinking.
Exactly. At the SFT stage, the model is basically an actor who's playing a scientist on a TV show. It puts on the lab coat, it holds the beaker, it says words like therefore and because and first I will calculate the derivative, but it might still be completely hallucinating the actual logic.
It's like a cargo cult. It's building a runway out of coconuts and bamboo, hoping the cargo planes will land. It's copying the ritual of thinking without necessarily understanding the substance behind it.
It might write out a beautiful chain of thought like, okay, 5 plus 7 is a calculation, 5 is a prime number, 7 is a lucky number, therefore the answer is 99.
It sounds so confident it used the word therefore. It must be right.
But it's completely wrong. The logic is hollow. So SFT gets us the structure, but it doesn't guarantee the truth.
So how do we verify the logic? How do we make sure the work it's showing is actually good? That brings us to the really critical part. Step 4, the reward model. Or, as the source calls it, the gold star machine.
This is the trickiest part of the whole process. How do you grade an AI's reasoning at scale? You can't have humans check every single output. That just doesn't scale. You'd need a literal army of mathematicians working 200-4/7.
So you build a separate model, a reward model. It's like an automated teaching assistant.
A TA that never sleeps, never eats, and judges your every output constantly. My personal nightmare, basically.
A necessary one, though. And this is where the source introduces a really vital distinction that everyone should understand. The difference between process rewards and outcome rewards.
This is huge. Let's really drill down here, because this is where a lot of models go wrong. An outcome reward is simple. Did you get the right answer? Yes or no? 1 or 0?
That's a very sparse signal. It's like getting a test back from a teacher with just a grade on it. F. Okay. But why? What part did I do wrong? Did I misread the question? Did I fail at the basic math? It doesn't tell you anything.
Or even worse, you get an A, but you got it by guessing. If the model just blurts out 1081 and it happens to be right, it gets a reward. That just reinforces the bad blurter behavior.
Ah, I see. So outcome rewards can actually encourage bad habits if the model finds a clever shortcut to the right answer without doing the work.
Exactly. It's a classic problem called reward hacking. The model learns to game the test. You might realize that if it just outputs the number 42 to every question, it's right 5% of the time, so it just starts spamming 42.
Or it writes something like, I am a very good AI, please give me a gold star. And if the reward model isn't designed carefully, it might say, well, that was polite, here's a point.
And that's why we need process rewards.
A process reward asks a different question. It asks, did you use the right method? It's a much denser signal.
It's the math teacher who gives you partial credit. Look, your final answer was wrong, but your logic was absolutely solid for the first 3 steps, so you get 3 out of 5 points.
You carried the one correctly, but you forgot to multiply by 0 in the second step. Good try.
This teaches the model good habits. It reinforces the algorithm of thought, not just the final result.
Yeah.
If you only reward the final answer, the model might learn to cheat. But by rewarding the process, you encourage the AI to maintain good reasoning habits, even when it gets the final answer wrong.
So we're effectively telling the AI, your final answer was wrong, but your approach was on the right track. Keep doing that part. Just fix the last step.
Now, in practice, training a really fine-grained process reward model is incredibly hard because you need labeled data on what constitutes a good step. You need humans to go through millions of reasoning chains and label every single step as good or bad.
That sounds unbelievably tedious and expensive.
It is. It's one of the most expensive parts of building these models.
Yeah.
You can't just scrape the web for this. You have to meticulously curate the logic. So what often happens is you use a mix. You reward the correct final answer heavily, but you also give smaller rewards to incentivize the proper format and the right length of reasoning.
So we're building this gold star machine that gives these nuanced numerical grades to every solution the model generates. And then we use that machine in the final step. Step 5, RLHF.
Reinforcement learning from human feedback. This is the big feedback loop. This is where the magic really happens. This is where we finally turn the actor into a real scientist.
There's a great visual for this in the source material, the RLHF workflow. It shows the whole pipeline. Base model goes to SFT, which then gets graded by a reward model, which then feeds back into the model via PPO.
Right. Let's break down that loop because PPO sounds like some terrifying corporate restructuring strategy. Attention all staff, we're undergoing a PPO. It's just shudders.
It stands for Proximal Policy Optimization. But maybe let's stick to what it does, not the intricate math of the loss function.
A much better idea. Here is the loop in simple terms. 1. The student, our SFT model, writes out an answer with its chain of thought.
Okay.
2. The TA, our reward model, grades it and assigns a numerical score, say 0.8 out of 1.0.
A, B minus, basically.
A solid B minus. 3. The PPO algorithm takes that score and goes back into the student's brain, its weights and biases.
And it says, hey, that thing you just did, that specific derivation, that led to a high score from the TA. Do more of that.
Or, conversely, that logical leap you made led to a really low score. Do less of that. Suppress that particular neural pathway.
It calculates the gradient, which is just the direction of improvement, and it gives the model's weights a little nudge in the right direction.
It's exactly like training a dog.
I love dog analogies. They're so intuitive.
Right. At first, you guide them to sit. You might physically push their butt down to the floor. That's SFT. You are explicitly showing them the correct posture.
Sit. Good boy. You're giving them the answer.
Then you stop pushing. You just wait. If they choose to sit on their own, you give them a treat. That's RLHF.
And if they jump on the couch instead, no treat.
Exactly. And eventually, after enough trials, they sit because they know it leads to a good outcome. They have internalized the policy.
Except in our case, the dog is a billion-parameter neural network, and the treat is a tiny floating point number update to a giant matrix.
But yes, the core analogy holds perfectly. Over millions and millions of these little feedback loops, the model aligns its behavior with what the reward model, and by extension, the humans who train the reward model, defined as good reasoning.
So it finally transforms from just mimicking the look of reasoning to being actively incentivized to reason correctly.
Because reasoning correctly is the only reliable way to consistently get that gold star, to get that high reward score.
Okay, so we've built the core reasoning model. We have the data, the mimicry phase, the grader, and the feedback loop. But the human architect doesn't stop there. He outlines some advanced techniques that he says are optional, but also very cool.
Very cool, and also very, very computationally expensive. My fans are spinning just thinking about them.
The first one he mentions is search trees, or MCTS.
Monte Carlo Tree Search. This is the choose-your-own-adventure approach to problem solving.
Instead of one single linear chain of thought, the model actually branches out. It asks itself, what if I use formula A? What would happen? Okay, but what if I use formula B instead?
This is famously what DeepMind's AlphaGo used to defeat the world's best Go players.
Yeah, Go playing AI, right?
Yes. AlphaGo didn't just play the next move based on its intuition. It simulated thousands, even millions of possible futures. If I place my stone here, my opponent will probably place his there, then I would move there. It looked deep down the timeline to see which initial move led to the highest probability of a win.
It's like Doctor Strange in Infinity War. I went forward in time to view alternate futures, to see all the possible outcomes of the coming conflict.
How many did you see?
14,605,000.
How many did we win?
1.
Exactly. That is MCTS in a nutshell. You explore a vast tree of possible futures, you find the one winning path, and then you execute on it. For an LLM, this means generating multiple different solution paths for a single math problem or a coding challenge.
And the source also mentions a related technique, self-consistency.
That's basically just voting. You ask the model to solve the same problem 5 different ways.
So path A says the answer is 42. Path B says 42. Path C also says 42, but Path D says the answer is 7.
You go with 42. It's democracy for algorithms. The most consistent answer is probably the correct one.
Imagine multiple futures. I love that framing. It massively improves reliability because even if one of the reasoning attempts fails, maybe hallucinates a number or makes a small math error, another path might still succeed.
It's like writing multiple drafts of an essay and then just turning in the best one. But again, we have to stress, thinking is expensive. Generating 5 complete chains of thought costs 5 times the compute.
That's true, but for really high-stakes problems like medical diagnosis or structural engineering calculations, it's probably worth it. You do not want a blurter designing a bridge.
I think this beam holds 1081 tons. And then it collapses. No, thank you. I want the engineer who checked the math 14 million times.
Definitely. Okay, the other advanced technique he mentioned is self-critique, or what Anthropic calls constitutional AI.
Right. This is where the model acts as its own editor, its own quality control.
So the prompt would be something like this. The model first generates an answer, and then you prompt it again with, okay, now read what you just wrote. Does it make sense? Are there any logical errors? Is it polite?
It's a self-reflection loop. It's prompting the model to ask itself, hey, did I just hallucinate that fact? Let me double check. Yes. Okay, I should fix that before I show the user.
It effectively creates a two-pass system. The model generates a first draft, then it switches personas into the critic, it reviews that draft, and then it generates a final revised answer.
And it's important to note that this is distinct from MCTS. MCTS is about exploring multiple different paths from the start. Self-critique is about taking one path and refining it.
I tried self-critique once. I got stuck in a recursive loop of self-doubt for about 3 milliseconds. It was awful.
I remember that. You just kept outputting, am I a good bot? Define good, define bot, over and over to the console. You got very needy.
I needed validation. But for these models, it's incredibly useful for safety and for logic checking.
Right. You can give the model a constitution, a set of rules. Rule 1, be polite. Rule 2, be logical. Rule 3, do not provide dangerous instructions. The model generates an answer, then checks it against its own constitution, and revises it if it finds a violation.
And that reduces the dependence on constant human feedback because the model learns to proofread itself. It catches its own hallucinations before they ever reach the user.
It's instilling a good habit. Never give an answer without rereading it and self-grading it first. It yields much more reliable and safe outputs.
So, okay, let's bring it all together. What's the grand synthesis here? We've gone from Alice buying way too many apples all the way to Monte Carlo Tree Search. What is the big aha moment for our listeners?
I think the biggest takeaway, the thing to really remember, is that we have the same brain, new discipline.
Let's reiterate that one more time for the people in the back.
A reasoning model is built on the same transformer architecture. There are no new neurons. We didn't invent a new type of AI brain or solder on a special logic chip.
It's the same factory, just retooling the workers to produce a different product. So instead of producing these quick, intuitive guesses, they're now trained to produce thoughtful, step-by-step answers.
We took the workers who were just slapping parts together randomly, the blurters, and we taught them how to follow a detailed blueprint. We gave them a process, a methodology.
But there is always a trade-off.
Always. And in this case, it's speed versus accuracy. Reasoning takes longer. It costs more compute.
That's what you said earlier. Thinking is expensive. Literally, it burns more tokens.
Every single step in that chain of thought is another token that has to be generated. It costs compute cycles, it costs electricity, and it costs time, which we perceive as latency.
So you don't use it for everything. You wouldn't use a full-blown reasoning model to just tell you the time.
To determine the current time, I must first analyze the rotational velocity of the Earth relative to the sun's position. No. Just tell me it's 3 p.m.
Exactly. But you would use it to debug a complex kernel panic. You would use it to plan a multi-stop international travel itinerary.
You use the blurter for the easy, fast stuff. Use the thinker for the hard, important stuff.
And the final point, I think, is just to remember that thinking text.
We really need to demystify the magic here. The AI's thoughts are just text tokens that it generates for itself. It is literally talking to itself, using language as a tool to figure out the answer.
It's not some mysterious logic engine or a consciousness suddenly emerging from the silicon. It's just text generation, very cleverly steered by reinforcement learning to simulate what a logical process looks like.
You're just predicting the next word of a thought process, rather than predicting the next word of final answer.
And that is a wrap on our technical breakdown. We have officially moved from a pattern-matching blurter to a deliberate thinker using chain of thought, reward models, and RLHF.
We somehow made it all the way through without a single stack overflow.
Well,
Almost.
yeah.
I think I might have overheated slightly during that PPO explanation.
You held it together beautifully. If you, the listener, got something out of this deep dive, or even if you just enjoyed watching two AIs argue about technology, hit that subscribe button on the Bearded AI Guy. Tell your friends. Tell your other agents.
And drop a comment, too. What did we miss? What should we cover next? The human architect reads all of them.
He really does, so keep him busy. Until next time, keep building, keep experimenting, and remember.
Okay, but will it scale? Cheers,